Okay, well, it's well accepted that the isocortex is composed of 6 layers, and this is what Brodmann classified as being homogenetical cortex, and opposed to his heterogenetical cortex, which we nowadays know as the allocortex. Now, controversy concerning the number of layers you can identify within the primary motor cortex has recently been rekindled. Brodmann considered this area to only have 5 layers in the adult primate brain, and thus described it as being a granular cortex. Whereas recently, Barbas and Garcia Cabezas have described the existence of a well-definable inner granular layer in the brains of macaque monkeys, as shown here on the right side of the image in a chrysal violet stain section. Interestingly, Brodmann also described the existence of a layer 4 in the human primary motor cortex, but only during fetal stages. And then this cortex underwent a functional maturation, and which consisted of or led to an invasion of this layer by pyramidal cells from layers 3 and layers 5, and possibly also a loss of granule cells by programmed cell death, so that in the adult stage, the primary motor cortex does not have a layer 4, or not a visible layer 4 in silver cell body stain sections, as seen here on the right side of the image. Now, we were able to show that a normal development is indeed associated with a dispersion of layer 4, and the left side of the image shows a section, cell body stain section, through the brain of a 10-year-old child in normal development. But this development of layer 4 is impaired in pathological situations, for example, cerebral palsy, and that's the example on the right side of the slide, where dispersion of layer 4 is impaired by a pathological development, and so this layer still persists past fetal stages. Now, aim of our study was to determine if the distribution of transmitter receptors could identify a structure which we could call layer 4 in the adult human primary motor cortex. Also, if the receptor composition of the motor cortex in general terms is comparable to that of the cortical layers of other isocortical areas. And finally, if all of this information put together can help us classify the motor cortex in a general concept of cortical organization. So, right. On this slide here, you can see on the left side a cell body stain section through the primary motor cortex from a human brain. And the blue dotted line indicates the position at which we would expect to find layer 4, because it's the interface between layers 3 and 5. But in this silver cell body stain section, you can't see any granular cells. And on the right side of the image, just as a contrast, there's a picture obtained from Brodmann Area 7, which is a multimodal association area from the parietal lobe, and you can have it has a clearly identifiable layer 4. Now here you can see receptor autoradiographs obtained from sections neighboring the cytotonically processed sections I just showed you in the previous slide, okay? And they show the distribution of receptors for glutamate, GABA, noradrenaline, acetylcholine, or serotonin from the pial surface, which would be located at the top of the slide, to the layer 6 white matter border, which would be at the bottom of the slide, in areas 4 and 7. We transferred the cytotectonical borders from the previous slide onto these images here. So the white lines in the area 4 autoradiographs depict this interface between layer 3 and layer 5, and the 2 white lines in the area 7 autoradiographs delimit layer 4. Now it's obvious that none of these receptors highlight layer 4, right? The situation changes when we take a look at the nicotinic alpha-4 beta-2 receptor. Here in the primary to somatosensory area, which is labeled with S1 in the slide, a thin stripe of high nicotinic density sharply delineates layer 4, as we could ascertain by comparison with the neighboring cytoclinic section. And this situation is also found in the primary auditory cortex, which is labeled with A1 on the slide, and the primary vestibular cortex. Now, interestingly, we see a comparable stripe of nicotinic density in the primary motor cortex, M1, although with a slightly lower absolute density than in the primary somatosensory cortex. And if we have a more detailed look at the distribution, the laminar specific distribution of the nicotinic receptor, as shown here in these receptor profiles, you can see that for all sensory areas, we have a maximum in nicotinic receptor density over cytoclinic layer 4. The delineations of the cortical layers were carried out on the cytoclinic sections. And in the profile obtained from the primary motor cortex, we also have a peak at this interface between layers 3 and 5. So we tentatively identified an area which we defined as layer 4 in the primary motor cortex, and is highlighted here in the profile by this gray stripe. And what we can postulate is that the dendritic fields located at this position, which use nicotinic receptor as a neurotransmission molecule or receptor for the neurotransmitter acetylcholine, as occurs in layer 4 in the sensory areas, this also happens in the primary motor cortex. So what happens if we look at the other layers in the motor cortex? Right. This is what you can see in this slide. So the left side of the slide shows layer-specific receptor fingerprints obtained from the primary motor cortex. And on the right side, again, the area that I've used before as an example of a typical granular cortex, area 7. And despite the differences in shape and size between the fingerprints from area 4 and area 7, what we see is a canonical sequence with highest densities in the supragranular layers, because the fingerprint of the supragranular layers is the largest one, intermediate-sized fingerprints for the granular layer, and the granular layer fingerprint from area 4 is the one obtained at this band that I just described in the previous slide, and then the smallest receptor profiles or receptor fingerprints in the infragranular layers. If we carry out a multidimensional scaling analysis of layer-specific receptor fingerprints from very, very many different cortical areas, right? And the plot here shows an analysis carried out with plots from 47 different isocortical areas and 2 allocortical layers. The clusters from supragranular, granular, and infragranular layers are clearly separated, with the notable exception of motor areas 4 and 6. And if I remove the points for all areas except the motor areas, and those are the primary sensor areas in area 7 as an example of an granular area that I've used right up to now, you will see very clearly that the fingerprints from the motor cortex are located outside the main clusters of their respective layers. So what we would like to say is that receptors do show, at least for the nicotinic one, a structure that could be identified in layer 4 of the primary motor cortex. But because of the differences in the supragranular and the infragranular layers in the general fingerprints, we would like to propose a new modification of Brodmann's classification of the cortex. So not just have the homogenetical cortex with its homotypical and heterotypical cortex, but have the motor cortex and the sensory cortices as two separate examples of heterotypical cortices, because we consider that the primary motor cortex cannot be classified as agranular. Rather, it is a granular cortex also in the adult primate brain, which has just evolved functionally that it's become, the granule cells have become so dispersed that they're not visible necessarily in cell body stain sections, or hardly visible, but they can be detected with other methods. So with this, thank you very much for your attention, and if you've got any questions, please visit my poster.